Ready for another deep dive? Today we're wading into the world of algebraic geometry, and, you've given us quite the paper to untangle.
It is a bit of a mouthful, isn't it? Families of pairs of genus 2 curves with isomorphic unpolarized Jacobians. Quite a title.
It's a good thing we've got you here to help us break it down. So for those of us who didn't spend our days pondering curves and Jacobians, what's the core idea here?
Well, at its heart, this paper is about uncovering hidden connections, relationships between geometric shapes that might appear quite different at first glance.
Okay, so we're talking about shapes, but like in a more abstract mathematical sense, not just triangles and squares, right?
Exactly. Imagine curves, but not just simple lines. Think of these curves existing in multidimensional space, their properties described by complex mathematical structures. And those structures, those are our Jacobians.
Jacobians, right. So if I'm picturing a curve, like a squiggle in space, the Jacobian is like a way to analyze it, to understand its unique fingerprint.
A perfect analogy. Now imagine you have two of these curves, distinct in their form, yet their Jacobians are practically twins. Almost identical, but with a slight twist.
Twins, but not identical twins.
You've got it. That's where the isomorphic unpolarized part comes in. It means these Jacobians share the same fundamental structure, the same DNA, so to speak, but they might express it in subtly different ways. And this paper, it dives into the exciting task of systematically constructing families of these curves with these almost twin Jacobians.
Okay, I have to admit, you've piqued my curiosity. So we're talking about more than just observing these relationships. We're actually talking about building them, creating them from scratch.
Precisely. It's about uncovering the underlying principles, the mathematical blueprints that allow us to generate these curves with their fascinating intertwined properties. And that's no easy feat.
So before we get into the specifics of how these curves are constructed, give us the why. Why should we care about these mathematical twins? What's the bigger picture here?
That's always the crucial question, isn't it? The beauty of this kind of research is that it's not just an intellectual exercise. The existence of these curve families, it hints at deeper symmetries, hidden structures within the very fabric of algebraic geometry. And understanding these structures can have ripple effects, implications that stretch far beyond this particular corner of mathematics.
We're talking about a potential paradigm shift then, like finding a secret passageway that leads to a whole new wing of the mathematical mansion.
Exactly. And who knows what other secrets we might uncover as we explore this new wing. The authors of this paper, they've outlined 3 different approaches, 3 theorems, each providing a unique blueprint for constructing these special curves.
3 different recipes for baking up these mathematical twins.
I like that. It's a delicious analogy.
Well, let's fire up the ovens. What does Theorem 1 have in store for us? Theorem 1 it is. Lay it on us. What's so special about this one?
Well, you see, this theorem, it goes beyond simply telling us that these curve families exist, It actually gives us a way to build them, a formula. It's like a blueprint.
So we're not just observing these relationships, we're like getting our hands dirty, constructing them from the ground up.
Precisely. The theorem focuses on a type of curve, labeled CD. And this formula, it lets us generate a whole family of these curves. Each one unique, of course. But here's the catch. For every CT curve we create, there's a mirror image, a seat, that always has this special, almost twin Jacobian.
Hold on. So we doodle a curve, flip it, and boom, its mirror image automatically has this twin-like Jacobian, no matter what the original curve looked like.
That's the beauty of it. This hidden symmetry, this predictable relationship between curves that on the surface seem totally different. It's pretty remarkable when you think about it.
Remarkable is an understatement. But I remember you mentioning some exceptions, right? These pathological cases. What's going on there? Do the rules just not apply?
Ah, yes. Those are the outliers, the edge cases. In these specific situations, and it depends on the mathematical field we're working in, those twin curves, they become, well, completely identical. The mirror image merges with the original.
So it's like the looking glass shatters, and we're just left with this single, unified curve. The twins become one.
A very poetic way to put it. But you're exactly right. It really highlights how interconnected these mathematical concepts are, how the very environment these curves exist in can influence their properties.
Okay, mind blown. But we've been talking a lot about the what, as in what these curves are, these relationships. I'm itching to understand the how. How do we actually construct these curves, and how do we know they have these properties? What's the math behind the magic?
That's where things get really interesting, where we dive into the nitty-gritty. One of the tools they use is called Cyclic Isogenies. Bit of a mouthful, I know.
Yeah, we might need a bit of a breakdown on that one. Cyclic isogenies, huh?
Think of them as maps Bridges connecting different elliptic curves. Remember those? The donut-shaped ones?
Yes. Elliptic curves. Always a favorite.
Right. Well, these cyclic isogenies, they give us a way to link these elliptic curves to study their relationships. But there's another piece to the puzzle, Galois restrictions.
Galois restrictions, now those sound a bit more intimidating. What do they do?
Well, imagine them as the rules of the game. They impose some order, some constraints, making sure our constructions don't just veer off into mathematical chaos.
So we've got bridges between these curves and then a set of rules to keep everything in check. Sounds like a high-stakes game of mathematical dominoes. But if this method is so great, why not just stick with it? Why bother with theorem 2 and 3?
An excellent question, and you're right, it is an elegant method. But like all things, it has its limitations. Think of it like having a recipe for a cake, but your oven only goes to one temperature.
Oh, I see where you're going with this. There's a but coming, isn't there?
Chuckles. There is. You see, this approach, this method of building twin curves with cyclic isogenies and these Galois restrictions, well, it hits a wall.
A wall, a dead end. Now you have to tell me more. A mathematical wall. You're going to have to elaborate on that one. What's stopping us?
So imagine we're using this method, right? Building our CT's curves, using these cyclic isogenies, but we're sticking with a specific degree, say degree 5, and we're working with the rational numbers. Here's the thing. Those Galois restrictions, they get really, really picky.
Picky how? Like, they limit what we can even build.
Exactly. It's like trying to build a house with a giant set of rules, and those rules say you can only use, like, one type of brick. With degree 5 isogenies, we're stuck. Only one elliptic curve fits the bill, and it has this special property, a J invariant of 2653.
Okay, so one option, and not a very exciting one at that. Sounds like we're at that dead end you were talking about.
Yep, pretty much. And here's the kicker. It doesn't get much better as we go up to higher degrees, like 9, 13, 25. The Galois restrictions, they just get tougher, less and less room to maneuver. Finding those twin curves with this method, it becomes near impossible.
So theorem 1, as elegant as it is, only gets us so far. What about our other options, theorem 2 and 3? Do they hit the same wall?
They take a different route, sure. But at the end of the day, they rely on the same principles. Cyclic isogenies, those Galois restrictions, they're still there. We might get a bit further, but ultimately, we're likely to encounter those same roadblocks.
So what now? Do we just throw in the towel, give up on finding more of these special curves?
Not at all. This is where things get really interesting. Limitations, they often spark new ideas, new approaches. The paper even hints at some. We've been working with rational numbers, right? But what if we branched out? Explore different number systems.
No, change the rules of the game entirely. See if that gets us moving again.
Precisely. By shifting our perspective, looking beyond the familiar, we might find those Galois restrictions loosen their grip a little. Maybe, just maybe, a whole new class of curves with those amazing twin-like properties are waiting to be discovered.
A mathematical treasure map, hidden in plain sight. Well, there you have it, folks. From the elegant symmetry of theorem 1 to the tantalizing limitations we've encountered, it's clear there's a whole lot more to explore in the realm of algebraic geometry.
Absolutely. And that's the beauty of mathematics, isn't it? Every answer leads to new questions, new avenues of exploration. Who knows what other hidden connections, what other mathematical wonders are waiting to be unearthed? The journey continues.
It certainly does. And for all our listeners, that journey doesn't have to end here. What other symmetries, what other hidden relationships are lurking out there in the vast world of algebraic geometry? We'll leave you with that thought. Until next time, keep exploring.
All right, so you sent over this research paper, Families of Pairs of Genus 2 Curves with Isomorphic Unpolarized Jacobians. Sounds intense.
It is a bit, yeah. But the core ideas, they're actually pretty fascinating. Really, it's about finding hidden connections between mathematical objects,
Okay, I like where this is going. Hidden connections, like what? Give me an example.
So imagine you're trying to crack a secret code. This paper's kind of like that.
Okay, I love a good code. So how do we crack this one? What's the key?
Well, it all starts with these things called Genus 2 curves. Ever seen them visualized? They look like donuts, but with an extra hole.
Donuts with 2 holes. Okay, I think I can visualize that. But why Genus 2 curves? What's so special about them?
It's all about their shape. You see, a regular donut, one hole, that's a Genus 1 curve. But Genus 2, those extra holes, they add complexity. Makes them mathematically interesting.
Got it. More holes, more math to do. But this paper you sent, it talks about pairs of these curves. What makes a pair special?
It's all about their Jacobians. Think of it like a fingerprint. Each curve has a unique Jacobian, and it helps us understand the curve in more detail.
Hold on, let me see if I'm following this. Each of these double-hole donuts, they have a unique fingerprint. And this fingerprint, it's called a Jacobian.
Precisely. But here's the thing. A Jacobian isn't actually a simple shape like a donut. It's what mathematicians call an abelian variety, which is a bit more abstract.
Abstract how? Can you give me something a little less, mathy?
Sure. Imagine you have a map. A polarized Jacobian is like that map with a big "you are here" marker. It gives you a fixed point of reference. But an unpolarized Jacobian, that's like the same map, but without that marker.
Okay, so you can still study the terrain, explore all the features, but you don't have that one fixed point to guide you. Interesting.
Exactly. And this paper, it's all about unpolarized Jacobians. The researchers, they wanted to figure out how to create pairs of these genus 2 curves, pairs that had the same unpolarized Jacobian.
So like finding two totally different looking maps that somehow describe the same terrain. How do you even go about doing that?
Well, they use these clever mathematical tools called Isogenies. Think of an isogeny as a special kind of map, a map between two curves. But it's not just any map, it preserves the structure of the curves.
So we're talking about more than just like drawing lines on a map.
Yeah.
These isogenies, they actually change the shape of the curves themselves.
In a way, yes. It's kind of like stretching or squishing a donut. You're changing its shape, but you're not tearing it or adding any new holes. It's still fundamentally the same kind of object.
So we're stretching and squishing these double-hole donuts, trying to find pairs that have matching fingerprints. I gotta say, this is some pretty high-level math we're talking about.
It is, but it's actually a very elegant approach to a complex problem. And you're right, it's not just random trial and error. There are rules.
Rules like what?
This paper focuses on isogenies of very specific degrees. Think of the degree like the strength of a magnifying glass. A degree 2 isogeny would be like looking at our donuts under low magnification, while a degree 7 isogeny would be like zooming in to see all the tiny details.
Okay, I'm with you. So higher degree means we're getting into the nitty-gritty details of these curves. But you said there were rules. What are they?
Right. So in math, you can't just go around stretching and squishing things willy-nilly. We need rules to keep things consistent. And that's where Galois restrictions come in.
Galois restrictions. I have to admit, that one's new to me.
Essentially, they're like guidelines or constraints to make sure that the mathematical objects we're working with, they behave themselves. Think of them like the laws of physics, but for math.
Okay, so if we break these Galois restrictions, our whole donut universe could implode.
Not quite implode, but things wouldn't make sense mathematically. The structures we build, they wouldn't be consistent. So Galois restrictions, they keep us honest, so to speak.
Gotcha. So we've got our donuts, our fingerprints, our stretching maps, and our mathematical rulebook. What did the researchers actually do with all of this?
Well, using those tools and working within those Galois restrictions, they were able to construct 3 families of these very special curve pairs. They outline it all in the paper in theorems 1, 2, and 3.
So these theorems, they're like the trophies they brought back from their mathematical expedition.
Exactly. But here's the really cool part. These theorems, they're not just descriptions. They actually highlight some really unexpected behavior.
Okay, now you've got me hooked. Unexpected how?
So they found these weird things happening with certain prime numbers, like 13 or 17.
Weird how? What's going on?
Well, remember how we were talking about those cooked pairs with the same Jacobian? Turns out when you start working with certain prime numbers, those pairs, they start behaving really strangely. Like those primes unlocked some hidden connections.
Okay, hidden connections, prime numbers, strange behavior. You got to give me more than that. What kind of strange behavior are we talking about?
Right, so take theorem 1, for example. That one's all about isogenies of degree 2. Now, most of the time, the curves they create using this method, they're distinct, meaning they're not isomorphic. They don't have that same Jacobian fingerprint.
Okay, so far so good. Distinct curves, different fingerprints.
Right. But then they plug in this very specific equation. It's tor plus 2t equals 12. And suddenly, boom, when they're working with the prime number 13, those curves, they become isomorphic. Same fingerprint out of nowhere.
So it's like the prime number 13 is some kind of magic key that unlocks this hidden relationship between the curves.
That's a great way to put it. And that's what makes this kind of research so exciting. It's like you think you understand the rules of the game, and then bam, something unexpected happens.
Yeah, those unexpected discoveries, those are the best kind. But what's the significance of these isomorphisms? Like, Why does it matter that these curves become the same when you're working with the prime number 13?
That's the million-dollar question, right? On the surface, they might seem like just mathematical curiosities. But these kinds of unexpected connections often point to deeper truths in mathematics. Sometimes even in other fields like physics or cryptography.
So these double-hole donuts, they could be hiding secrets about the universe. That's pretty wild.
You never know. But for now, let's get back to those theorems. Each one, it describes a whole family of these curve pairs. And each family, it's defined by specific equations.
So like, if I were a math whiz, I could take these equations and actually visualize these curve pairs, see how they're related.
Exactly. And the really interesting part is, these relationships, they can change depending on what's called the characteristic of the field you're working with. Remember those Galois restrictions?
The rules of the game, yeah, I remember.
Well, those rules, they can change depending on the number system you're using. It's like playing the same game, but on different playing fields.
So what you're saying is the relationships between these curves, they're not set in stone. They can change depending on the mathematical environment you're working in.
Precisely. And that's what the researchers found so intriguing. They were very successful in constructing these curve pairs with isogenies of degree 2, 3, 4, and even 7 when they were working with irrational numbers. But when they tried to go higher.
Higher, as in isogenies of degree 8, 9, and so on.
Exactly. That's when they hit a wall.
A wall. Like they just couldn't do it. What kind of wall are we talking about here?
Well, it all comes back to those Galois restrictions. They found that when you start dealing with isogenies of higher degrees over the rational numbers, those restrictions, those rules, they become incredibly strict.
So it's not that it's impossible to find these curve pairs with higher degree isogenies. It's just that the search space becomes incredibly small.
Exactly. It's like trying to find a needle in a haystack, but the haystack keeps growing exponentially.
That doesn't sound very promising. Does this mean that exploring these higher degree isogenies is a dead end?
Not at all. Remember, this research was specifically focused on the rational numbers. But there are tons of other number systems out there, each with its own set of Galois restrictions, its own rules of the game.
So it's entirely possible that these higher degree isogenies are much more well-behaved in other mathematical landscapes.
Exactly. And that's what makes this kind of research so exciting. It opens up a whole new world of possibilities. It's like we've explored one little corner of the mathematical universe, and now we're realizing just how vast and mysterious it really is.
And who knows what other strange and wonderful discoveries await us out there. So it's like we've mapped out this one little island, but there's a whole archipelago out there waiting to be explored.
Exactly. And who knows, maybe those other islands, those other number systems, they hold the key to understanding these higher degree isogenies.
Like we're at the edge of a mathematical frontier. Exciting stuff. But I have to admit, all this talk about curves and Jacobians and Galois restrictions, it's a lot to wrap my head around. So for those of us who aren't, math geniuses, what's the key takeaway from all of this?
Well, I think the biggest takeaway is just how much we still don't know. Even in a field like algebraic geometry, which has been studied for centuries, there are still these mysteries waiting to be uncovered.
And that even the things we think we understand, like the relationship between these curves, they can change depending on the mathematical framework we're using.
Exactly. It really highlights the power of perspective in mathematics and the importance of always questioning our assumptions.
Because those assumptions, they could be limiting our understanding, holding us back from making even bigger discoveries.
Precisely. And who knows what practical applications those discoveries might have.
Right. It reminds me of that quote, "It is impossible to be a mathematician without being a poet in soul."
I like that. It speaks to the beauty and elegance of mathematics, don't you think?
Absolutely. And to the importance of creativity and imagination. Because at the end of the day, that's what drives mathematical exploration.
Couldn't have said it better myself.
So to wrap things up, we've journeyed into the world of genus 2 curves, explored their unique properties, and learned how mathematicians are using these things called isogenies to uncover hidden relationships. We've even dipped our toes into the sometimes confusing world of Galois restrictions.
And through it all, we've seen just how much more there is to discover, how much more we can learn about these curves, about number systems, about math itself.
Exactly. It's been a wild ride, and it's really opened my eyes to the beauty and complexity of this field. So to our listener out there, if you're as intrigued by this as we are, don't be afraid to dive in and explore further. You never know what amazing discoveries you might make.
That's right. Curiosity is the engine of progress. Keep asking questions, keep exploring, and most importantly, never stop being amazed by the wonders of mathematics.
That's a perfect note to end on. Until next time.
All right, get ready, because today we're diving headfirst into some advanced geometry.
Oh, wait.
We're talking about something called genus 2 curves and how they connect to these things called elliptic curves.
Okay.
And you've given us a research paper to work with that has, well, let's just say it has a title.
It's a bit of a mouthful.
Yeah, a little bit. Families of pairs of genus 2 curves with isomorphic unpolarized Jacobians.
Yeah, definitely not something you'd hear in everyday conversation.
So for someone who maybe hasn't been exploring the world of advanced geometry lately, what are we even talking about when we say genus 2 curve?
Imagine a donut. You got that.
A donut? Yep, I can picture that.
Okay, so in math, we would say that a donut has genus 1.
Because it has one hole.
Exactly. Now take that donut and imagine twisting it around to make a pretzel.
Okay, I think I see where you're going with this.
Yeah. So a pretzel with its 2 holes would have genus 2. And these curves we're talking about are like the pretzels of the math world. They're way more complex than your average circle.
So they're kind of like the mathematical equivalent of trying to make sense of a pretzel dough.
In a way, yes. And because they're so complex, we need clever ways to study them.
Which is where I'm guessing these Jacobians come in.
You got it.
Although I have to admit, the word makes me think of something you'd find in like an antique shop.
It's more like taking something really complicated and finding a way to make it simpler.
Okay, so how do we simplify these pretzel-like curves?
Think about listening to a symphony, right? You've got all those instruments and notes all swirling around.
Yeah, a whole lot going on.
Imagine you could take that whole symphony, the entire sound, and map it to a single point in space. That's what the Jacobian is like.
Wow, so it's like taking all that complexity and boiling it down to its essence.
Precisely. Instead of trying to untangle each note, you just analyze that one point that represents the entire sound. Much easier to handle.
That's a pretty neat trick, so we don't have to be musical geniuses to appreciate the symphony.
Exactly. And now imagine you have 2 different symphonies, and their corresponding points, they're Jacobians, they have this special relationship, and we call that an isogeny.
Okay, isogeny, another word that sounds like it has its own dictionary entry.
I know, but it's not as complicated as it sounds.
So what are we talking about when we say 2 Jacobians have an isogeny between them?
Think of it like 2 different musical scales, one starting on C and the other starting on, let's say, F sharp.
Okay, so they sound different.
Exactly. But the relationship between the notes, the intervals, those are the same, and that's kind of like what an isogeny is between elliptic curves.
Hold on, elliptic curves. I thought we were talking about genus 2 curves. Are we changing gears already?
Not quite. Think of elliptic curves like the simpler cousins of our genus 2 curves.
Like single notes compared to a whole symphony.
You got it. What's really interesting is that we can use these simpler curves and this idea of isogeny between them as a tool to understand those more complex genus 2 curves.
So we're using the simpler curves as stepping stones to explore the more intricate ones.
Exactly. It's like using a map to navigate a complex maze.
So by studying these isogenies, we're essentially mapping out the relationships between these curves, kind of like charting constellations in the mathematical universe.
That's a great way to put it. It's all about uncovering hidden connections.
Okay, that's incredibly cool. So where does this research paper fit into all of this? What's it adding to our understanding?
Well, this paper focuses on creating pairs of those genus 2 curves, specifically ones where the Jacobians have that special isogeny link we were just talking about.
So it's like a recipe book for creating specific combinations of these curves with their sounds, or I guess I should say their Jacobians, linked in this special way.
That's a very musical analogy. I like it.
I'm all about the music analogies today, apparently.
And just like a good recipe, the paper breaks down this construction technique step by step.
Okay, before we get to the recipe itself, there's one more ingredient we have to understand, and that is Galois restrictions. It sounds a bit intimidating, if I'm honest.
It's not as scary as it sounds. Think of them like a set of rules that tell our curves how to behave.
Rules for mathematical objects, interesting. So what kind of rules are we talking about here?
These rules basically dictate how our curves operate over different number systems. Remember those alternate dimensions you mentioned earlier?
Okay, right. Different number systems, not just our familiar 1, 2, 3s.
Exactly. We're going beyond basic math here, and these Galois restrictions are crucial because they help us determine whether the pairs of curves we're building are genuinely different, like 2 completely different pretzels.
Not just 2 donuts with different frosting.
Exactly. It's about making sure we're dealing with the real deal, not just cheap imitations. We want to understand the true nature of these curves and how they're related to each other, and these restrictions help us do just that.
So we're using these restrictions to avoid accidentally creating mathematical clones? This is all starting to come together. Okay, let me see if I've got this straight. We have these genus 2 curves, our pretzels, if you will.
I like where this is going.
And we study them by looking at their Jacobians, which are kind of like their unique sonic fingerprints. This paper is all about finding pairs of these curves that are linked by these isogenies, these hidden musical connections.
So far, so good.
And on top of that, we have to make sure we're not creating mathematical copies. So we use these Galois restrictions as our rule book.
You've got it. You're a natural at this.
Well, I've had a great teacher. Now, am I right in thinking that the paper then goes on to give some specific examples of these recipes?
You are indeed, and they call them theorems.
So instead of just one recipe, we get a whole collection of them, each one creating its own unique mathematical flavor. I'm ready to fire up the oven and get cooking. What does Theorem 1 have in store for us?
Well, this first theorem focuses on a very specific type of isogeny, one that has a degree of 3. Think of it like a musical phrase with 3 notes.
Ooh, I like the sound of that. A 3-note phrase, simple but elegant. A 3-note phrase, I like it. So this theorem gives us the blueprint for making these pairs of genus 2 curves that are linked by this degree 3 isogeny, this 3-note musical connection.
Exactly.
But what does the actual sheet music look like? What are we working with here?
It gives us an equation, and just like any good equation, it's got a variable. In this case, it's tret.
Okay, tret for theorem, I'm following this.
And by plugging in different values for t, we can unlock a whole bunch of genus 2 curves, all of them related by this degree 3 isogeny.
So it's like a master key that opens up a whole treasure chest of curves.
I like that, a master key.
But hold on a second. Don't those Galois restrictions we talked about earlier come into play here? Do they mess with our recipe at all?
They definitely add a little twist.
How so?
Well, remember, these restrictions are like the rules of the game, right?
Right, our mathematical rule book.
And because we're dealing with isogenies of odd degree, in this case 3, those Galois restrictions tell us that the discriminants of the related elliptic curves have to be squares.
Okay, hold on. Elliptic curves, discriminants, remind me again how those fit into all of this.
Sure, it's easy to get lost in the weeds a little bit. So remember, we're using those simpler curves, the elliptic curves, as tools to help us understand the more complicated genus 2 curves.
Right, like using a map to navigate a maze.
Exactly, and these discriminants, they're just special values that tell us something about the shape of those elliptic curves.
Got it, like a mathematical fingerprint for each elliptic curve.
Precisely. So those Galois restrictions are saying that those fingerprints, those discriminants, they have to be perfect squares for this recipe to work.
Interesting. So it's like saying our musical notes can only be played on certain keys of the piano.
A very musical analogy. And this condition, in turn, puts some limits on the genus 2 curves we can create with this specific isogeny.
So even though we have this master equation, those Galois restrictions are kind of narrowing down our options.
Yeah.
What happens when we try a different isogeny, maybe one with a degree of 4? Is that what Theorem 2 is all about?
You got it. Theorem 2 takes us to the world of degree 4 isogenies. Our musical phrase just got a bit longer.
And I'm guessing this change in degree from 3 to 4 also changes how those Galois restrictions affect our recipe.
That's a great observation. You're catching on quick.
So what's different this time around?
Well, because we're working with an even degree now, those restrictions actually loosen up a bit.
Oh, really? How so?
Instead of requiring those discriminants to be perfect squares, now they only need to differ by a square.
Interesting. So we have a bit more wiggle room this time.
Exactly. We still have those Galois restrictions shaping things, but within those boundaries, there's a lot more room to play around.
I like how you're bringing the music analogy back. It really helps make sense of all this.
Glad to hear it.
So we've covered degree 3 and degree 4 isogenies. What about theorem 3? What's cooking in that pot?
Theorem 3, no, that one's a little different. This is where we venture into uncharted territory with isogenies of degree 7, a prime number.
Ooh, prime numbers. Those always add a little intrigue to the mix.
Right. They have a certain mystique about them. And degree 7 is particularly interesting.
Why is that? What makes it stand out from the others?
Well, whenever we deal with isogenies of a prime degree that's bigger than 3, like 5, 7, 11, you get the idea.
Prime's greater than 3. Yep.
Those Galois restrictions we keep bumping into, they get really, really strict.
Stricter than before, even with the even or odd degree thing.
Way stricter, especially when we're working with rational numbers.
Rational numbers, those are just our everyday numbers, right? Fractions, decimals, that sort of thing.
Exactly. Those are the ones. But here's the thing. When we use these everyday numbers, those prime degrees that are bigger than 3, they really limit our options.
You mean because the Galar restrictions are being extra strict?
Exactly. It means there are only a very limited number of elliptic curves that fit the bill for this recipe to actually work.
So instead of having a whole family of curves to play with like we did before, we're suddenly down to just a handful.
That's exactly it. But it turns out for degree 7, we're actually pretty lucky.
Lucky how?
Well, even with those really tight restrictions, we can still find a family of genus 2 curves that checks all the boxes.
So degree 7 is like the exception to the rule.
Kind of. It's more like we just got really lucky with this one. Because when you go beyond degree 7, things get a whole lot harder, at least when we're sticking with those rational numbers.
So it's like we've hit the high notes and our voices are starting to crack a bit.
Something like that.
So we've explored these isogenies of degree 3, 4, and even the special case of 7, each one like its own musical scale, creating these fascinating families of curves. But it sounds like degree 7 might be the last note in our musical masterpiece for now. Have we hit a wall? Well, maybe not a wall exactly.
More like we've reached a fork in the road.
Okay, I like that.
We've taken this one particular technique about as far as it can go.
But that doesn't mean the journey is over.
Not at all. If anything, this paper just opens up a whole new can of worms.
Meaning what? What kind of questions are we left with?
What makes you wonder if there are other techniques out there, other recipes that could help us build these curved pairs with even higher degree isogenies?
So maybe there's a whole other set of mathematical tools we haven't even considered yet.
Exactly. Maybe we need to think outside the box a little, shift our perspective.
What do you mean?
Well, we've been so focused on these rational numbers, remember?
Oh, right. Our everyday numbers.
But what if we took a trip into those other dimensions of numbers, the ones we talked about earlier?
You mean going beyond the familiar?
Exactly. It's possible that by venturing into those uncharted territories, we might be able to break free from the limitations those galore restrictions have placed on us.
So there's still a chance we can get past this degree 7 hurdle. We just need a new approach.
Precisely. And that's what makes this area of math so exciting. There's always something new to discover.
This whole deep dive has been quite the adventure. We've gone from picturing donuts and pretzels to navigating the complex world of genus 2 curves, and even uncovered these hidden musical connections between them.
And I think it all comes down to these elegant mathematical rules. Who knew math could be so musical?
It's pretty amazing when you think about it, and we've only just scratched the surface.
That's right. There's still so much more to explore, so many more secrets these genus 2 curves are hiding.
I'm definitely leaving with more questions than I came with, but in a good way. A huge thank you for taking us on this incredible journey through the world of genus 2 curves.
It's been my pleasure.
And for our listeners, until next time, keep exploring, keep questioning, and most importantly, keep diving deep into the fascinating world of mathematics.
Okay, so get this. We're diving into algebraic geometry today. Curves, right? But specifically, there's this paper linking together two types you might not think go together at all. Genus 2 curves and elliptic curves. Have you ever come across those before?
Probably without even realizing it, actually. Elliptic curves, I mean. They're big in cryptography these days.
Right, so it's not just abstract math then. They have real uses.
Oh, absolutely. Genus 2 curves, they're a bit more niche, but still important. String theory uses them, for example.
Okay, so big important stuff then. But getting to the point of this deep dive, this paper by Raghda Abdellatif, it's called Families of Pairs of Genus 2 Curves with Isomorphic Unpolarized Jacobians. That's got to be some pretty surprising stuff, right?
Totally surprising. What she's found is there are these pairs of genus 2 curves, and if you just look at them, they seem completely different equations, different geometry, the whole works. But here's the kicker. When you look at their Jacobians, something really strange happens.
Hold on, back up. Jacobians. What are those for people who don't speak fluent math?
It's like this. Think of a curve as a fingerprint, right?
Yeah.
Unique shape, properties, all that. The Jacobian, it's like you're extracting some specific info from that fingerprint. You're turning the curve's geometry into this thing, an abelian variety, which has its own little set of rules.
Okay, so we're like translating the picture into code, kind of.
Exactly. You got it.
So we take these two different looking curves, find their code, their Jacobians, and the codes match, even though we started with different curves.
You're getting it. There's a bit of a trick, though. To see the match, we have to kind of forget some of the Jacobian structure. It's called the polarization, like blurring the code a little to make the match.
Oh, that's wild. Like those hidden image things. where you unfocus your eyes and suddenly, boom, something new is
Yeah.
there. So Abdellatif's paper, it's finding these hidden connections. How does she even do that? What's the secret?
The secret weapon is something called an isogeny. Imagine a map, but instead of places, it connects elliptic curves. It keeps the curve structure intact in a special way. So Abdellatif, she starts with these isogenies, and then she uses them to create these subgroups, quotient structures. It's like high-level math origami, folding and cutting to make new shapes, and those shapes become her genus 2 curves.
Wow, so she's not just finding these curves, she's building them, using isogenies as the starting blocks, and she did this with a bunch of different curve families,
You
right?
got it. The paper looks at 3 families, degree 3, degree 4, and degree 7 isogenies. Those are the starting points, and they lead to these totally unique curve families.
Degree 3, 4, 7. Those are like the strength of the isogeny or something.
Yeah, you could think of it that way. The higher the degree, the more complex the map between the curves.
So degree 7 isogeny is like the superhighway compared to the scenic route of a degree 3.
Something like that. It's like comparing a waltz to a tango. Both have their own rhythm, their own complexity. What's really cool is that the type of isogeny, the dance, if you will, it actually affects what rules those curves have to follow, like a mathematical dress code.
Okay, now you've got to explain that one. A dress
Yeah.
code for curves.
Well, not literally a dress code, but think of it like this. When you're working with a degree 3 isogeny, or any odd degree 1, for that matter, there's a particular quirk. Remember those codes we were talking about, the Jacobians? There's a piece of info in those codes called a discriminant, and for these curves to work over our usual number system, that discriminant has to be a perfect square.
Whoa, hold on. Back up again. What in the world is a discriminant and why does it have to be a square?
You're right, I got ahead of myself. Let's try a different analogy. Imagine you're baking a cake, right? The ingredients, those are like the variables in an equation. The discriminant, it basically tells you if you're going to get a nice, smooth cake or a total disaster. Depending on what you put in, you might get a flat pancake or something totally crumbly and gross.
Okay, so the discriminant tells us if our math cake is going to be a winner or a disaster.
Yeah.
But what's this about it being a square? What does that even mean in this context?
Good question. It's all about making sure our curves play nicely with the rational numbers. You know, that's right. Fractions, whole numbers, the kind of numbers we use every day. Having a square discriminant, it's like a guarantee that our curves will behave themselves when we're working with those familiar numbers.
So it's a rule we got to follow to keep our math from going haywire.
Precisely. It's like a quality control check for our mathematical ingredients.
Got it. So square discriminant, check. Now this rule is for all the odd degree isogenies, not just the ones in this first family.
You got it. It's a general principle for the odd degree cases. But here's where things get interesting. When we move to the degree 4 family, things change up a bit. Instead of one discriminant needing to be a square, now we need the ratio of the 2 discriminants involved to be a square.
Wait, hold on. I'm getting lost. Instead of one thing being square, now it's the ratio. Like we're dividing them.
It's a bit like, instead of needing one perfectly square cake pan, we need 2 pans where one is exactly double the size of the other. The proportions have to be just right.
Okay, so changing that isogeny degree really throws a wrench into things. But we're still trying to make sure our curves work out nicely with the rational numbers. Like that's the whole point of these rules.
Exactly. And you know what's really neat? This change in the discriminant rule, it actually shows up in the equations for the degree 4 family. They have a different look compared to the degree 3 equations, kind of like how you can tell a cake made with oil from one made with butter just by looking at it.
Subtle differences, but important. So to recap, 2 families, each with its own isogeny, and those isogenies dictate these really specific rules about the discriminants, which then affects the whole structure of the equations for the curves. It's like a chain reaction.
That's a great way to put it. It's all connected like a delicate dance of mathematical structures.
A delicate dance. I like that. But don't leave me hanging. We've got one more family to cover. What happens when we crank that isogeny up to 11? Or, well, degree 7 in this case.
Degree 7, now you're talking. This is where things get extra spicy. Remember that rule about odd degree isogenies needing a square discriminant? Well, guess what? Degree 7 brings it back.
It's like we did a full circle. Waltz, tango, back to the waltz.
Exactly. But this time, the waltz is even more intricate, more demanding. The equation for this family is the most complex of the 3, reflecting that higher degree isogeny.
So, same basic steps, but way more advanced. Like, we need a math PhD to even watch at this point.
Something like that. But the cool thing is, even with all that complexity, the core idea is still the same. We're still dealing with these pairs of curves that seem totally different on the surface, but when you look at those unpolarized Jacobians, bam, they're a match.
It's like those spot the difference pictures, but for mathematicians. You got to know exactly where to look to see the connections. So we've got these families, these rules, these hidden connections. But why does any of this matter? Like the grand scheme of things, what's the point? That's the million-dollar question, right? We've been on this mathematical journey, but what's the destination? Why does any of this actually matter?
It's something mathematicians are always thinking about. Sometimes the beauty is in the math itself, but here there's more to it. This research, it shows us where our tools fail, in a way. Like, we use unpolarized Jacobians to study curves, right? But this shows there are limits to what they can tell us. It's like, imagine trying to identify someone from a blurry photo. You can tell some things, but not everything.
So the unpolarized Jacobian, it's like a blurry picture of our curve. Gives us some info, but not the full story.
Exactly. And what this paper shows is those special curves we talked about, the ones that look different but have the same unpolarized Jacobian. Any difference between them, it must be in the information that the unpolarized Jacobian doesn't capture.
Okay, now I'm really interested. Give me an example. What kind of differences are we talking about?
Think about something called the gonality of a curve. Basically, it tells you how complex the curve's shape is. Some curves are simple, like a circle, but others are all twisty and turn around a bunch. The gonality is like how many times you have to lift your pen to draw it. Turns out, the unpolarized Jacobian can't always tell curves with different gonalities apart.
So two curves, one simple, one super complicated, could have the same unpolarized Jacobian. That seems like a big problem.
It is. It means the Jacobian is powerful, but it has blind spots. Like,
Yeah.
You can't understand a whole person just by their shadow, right? You miss the details.
That's fascinating and a bit creepy, to be honest. Like there's a whole layer of math we're missing. But is that it then? Have we hit the end of the road with these curve families?
Not at all. Remember, Abdellatif used Isogenies of degree 3, 4, and 7. What about 8, 9, even higher?
Oh, good point. Is there something special about 7 then? Like that's the highest we can go?
It's not about the number itself, but what happens mathematically. Abdellatif, she mentions it gets really hard to go higher with the rational numbers. Remember those discriminant rules? The higher the degree, the harder those rules get to follow. It's like trying to squeeze a giant object into a tiny box.
So we're stuck. No more secret passages to find.
Not necessarily. That's just with rational numbers. Maybe if we change the rules of the game, use different kinds of numbers, those higher degree isogenies would work. It's like our mansion of math might have secret rooms we haven't found yet.
My mind is officially blown. We've covered so much ground. From genus 2 curves to elliptic curves, isogenies, Jacobians. And it sounds like this is just the beginning. So much more to explore. For our listeners who want to keep digging, what's something they can think about that builds on all this?
We talked about how these special curve pairs, they force us to look beyond the Jacobian, right? So here's a question. Are there other tools, other ways of looking at curves that could reveal even more hidden connections, a whole different way of seeing the math?
Now, that is a question to ponder. Seems like we're just scratching the surface of this whole area of math. Huge thanks to our expert for guiding us. And to everyone listening, stay curious, because the most exciting discoveries, they're often hiding in plain sight, just waiting for us to notice them.
Okay, so get ready to dive into a fascinating world. Like, sometimes you need more than just a glance to tell twins apart, right?
Yeah.
Well, imagine trying to do that with mathematical curves. That's kind of what we're dealing with here. These pairs of curves on the surface look different, but deep down, they share this fundamental connection.
That's right. We're diving into isomorphic unpolarized Jacobians. Bit of a mouthful, I know.
You can say that again. But before we get lost in the jargon, can you break this down for me? Like, what's so special about these Jacobians, and why should we even care if they're isomorphic or not?
Great question. Imagine you're trying to fingerprint a piece of music. The fingerprint itself won't tell you if it's jazz or classical, but it will tell you if two recordings are actually the same song, even if they're like played on totally different instruments. The unpolarized Jacobian is kind of like that fingerprint, but for a curve.
Okay.
It captures something essential about its structure. And when two curves have isomorphic unpolarized Jacobians, it means they share that same deep structure, even if they look totally different on the surface.
Okay, so I'm starting to get the picture. So finding these curve pairs, it's like we're discovering hidden musical connections. So what's the big reveal? Like, why does any of this even matter?
Here's where it gets really interesting. By finding these pairs, mathematicians can figure out what you can't tell about a curve just from its unpolarized Jacobian. It's like you can't tell someone's favorite color just by looking at their fingerprint.
Intriguing. So it's about understanding the limitations of this mathematical tool, this unpolarized Jacobian.
Precisely. It doesn't tell the whole story. There are like hidden depths to these curves, and finding these pairs is like shining a light on those hidden connections.
I love it when we uncover hidden mathematical connections. Okay, let me guess. Mathematicians have been on a quest to find these curve pairs, especially in the world of number fields, which I'm guessing is like your mathematical playground.
You're exactly right. Number fields are like the lifeblood of number theory. They're like mathematical universes that contain all the familiar numbers we know, plus some more exotic ones.
Nice.
Finding these curve pairs over number fields, it's like discovering new constellations in those universes. It helps us understand the structure of these mathematical objects in a much deeper way.
Okay, I'm hooked. Tell me more about this quest. How do mathematicians even go about finding these curve pairs with isomorphic unpolarized Jacobians? It sounds like a real mathematical treasure hunt.
Well, luckily for us, we have a treasure map of sorts, this paper, families of pairs of genus 2 curves with isomorphic unpolarized Jacobians by Raghda Abdellatif. It outlines some really clever techniques for constructing these curve pairs.
So Abdellatif's like our mathematical Indiana Jones leading us to these hidden treasures. What kind of tools does she use in her search?
Instead of whips and fedoras, she uses this powerful mathematical concept called Isogenies. Think of it like this. You have two rubber bands, right? And you can stretch or twist one to make it look like the other without tearing it. That transformation, that's kind of what an isogeny does with curves. It transforms one into another while preserving some of their essential properties.
Okay, so I'm visualizing these like mathematical rubber bands transforming and twisting.
Yeah.
But how does that lead us to those curve pairs with isomorphic, unpolarized Jacobians?
That's where the real ingenuity comes in. Abdellatif starts with simpler curves called elliptic curves. So imagine those are our rubber bands.
Okay.
And she uses isogenies to combine two elliptic curves in a specific way that creates this new surface called an abelian surface.
An abelian surface. Is that like a mathematical jungle gym?
It's more like a mathematical donut. A torus, to be precise. And this torus has special symmetries. Think of it like you can rotate it or flip the donut. It still looks the same.
Okay, I can picture that. A perfectly symmetrical donut, no matter how you turn it.
Exactly. Now, here's where the magic happens.
Oh.
By strategically folding this abelian surface, which in mathematical terms is called taking a quotient,
Fancy.
we can create those genus 2 curves we're after. It's like taking that perfectly symmetrical donut and carefully folding it in on itself to create this completely new, more complex shape.
So we're folding mathematical donuts now. This is getting interesting.
It is. It is.
But it still sounds pretty abstract. Does Abdellatif give us any concrete examples of these curve pairs?
She does. In fact, Theorem 1 in her paper lays out a whole family of these curves. It gives us an equation with a parameter t that acts like a tuning knob. So by plugging in different values for t, we can generate a whole bunch of new curve pairs with those twin-like unpolarized Jacobians.
So it's like a mathematical recipe where T is the secret ingredient. Give me a taste. Like, what makes this recipe so special?
What makes it fascinating is that T can't just be any random number.
Okay.
It has to follow certain rules called Galois restrictions,
Bro.
which are like specific properties that T must have, especially when we're working within those number fields we talked about earlier.
Galois restrictions. Okay, those sound intense. Like mathematical bouncers guarding the VIP section of number theory.
That's a great analogy. These Galois restrictions add a whole other layer of intrigue to the mix. And here's where it gets even more interesting. The Galois restrictions are actually different depending on the type of isogeny Abdellatif starts with. If the isogeny is of even degree, think of it like a rubber band being twisted an even number of times, we get one set of rules for T. But if it's of odd degree, those rules change.
So even versus odd isogenies lead to different families of curves. It's like having different mathematical universes governed by different laws of physics. Tell me more about these different families. What other treasures did Abdellatif unearth? So it's like Abdellatif stumbled onto this secret code, and the even or odd degree is the key to unlocking different parts of the mathematical mystery.
Exactly. And those codes, they lead to some pretty amazing discoveries. In Theorems 2 and 3, Abdellatif looks at these different families of curves, specifically the ones built from isogenies of degree 4 and degree 7.
Okay.
Each theorem's like a new chapter in our mathematical adventure.
Yeah.
They reveal like even more intricate patterns and connections.
So she's basically saying, Hold on to your hats, folks, because we're going even deeper down this rabbit hole.
Yeah, pretty much. But here's the real kicker. She found that sometimes, even if the curve's Jacobians are isomorphic, remember those mathematical fingerprints?
Right, right.
The curves themselves can be fundamentally different depending on the mathematical environment they're in.
Hold on, back up a sec. So two curves can share the same fingerprint, but still be different in some significant way. How is that possible?
Think about it like this. Imagine two recipes that produce cakes that taste exactly the same.
Okay, yeah.
But one uses butter and the other one uses oil. They might taste identical, but the underlying ingredients, the building blocks of those cakes, are different. That's kind of what's happening with these curves. Even though their Jacobians are isomorphic, the curves themselves can be constructed using different mathematical ingredients, depending on the number field we're working with.
Okay, that makes sense. It's like those look-alike, taste-alike contests where things seem identical at first glance, but when you really get down to it, there are these subtle but important differences.
Exactly. And it highlights this incredible complexity and nuance of these mathematical objects. I mean, we're just scratching the surface of understanding, like, all their hidden depths.
This whole deep dive has been mind-blowing, but it sounds like this method of using isogenies to construct these curve pairs, it's not exactly a walk in the park. Abdellatif mentioned something about obstructions. Did she hit some kind of mathematical roadblock?
In a way, yeah. It turns out this method kind of hits a wall when we try to use isogenies of degree 5 or higher, except for degree 7, which, as we've seen, works out nicely.
So degree 7 is like the lucky number in this mathematical lottery. What makes those other degrees so difficult?
It all comes back to those Galois restrictions, those mathematical bouncers we talked about before.
Right.
When we're working with the rational numbers, those Galois restrictions become incredibly strict for isogenies of degree 5 or higher. It's almost like trying to fit a square peg into a round hole. The rules just don't allow it.
So we've reached the limits of this particular technique, but it makes me wonder, are there other mathematical tools out there, other ways to construct these curve pairs that might, unlock even more secrets?
That's the beauty of mathematics. There's always more to explore, maybe by using different types of symmetries or venturing into the world of other number fields. We might discover entirely new families of curves with these fascinating properties.
It's like we've only explored one branch of a vast and intricate mathematical forest. Who knows what other wonders await us in those uncharted territories? This deep dive has been incredible. Thanks to Abdellatif's research, we now know that even in the abstract world of genus 2 curves, there are these hidden connections, these twin-like structures just waiting to be discovered. And who knows what other mathematical mysteries are out there just waiting for someone curious enough to unravel them.